Hi, this is Alex from devstories.eu. Async I/O, episode 16 of 20. When you use high-level async I/O streams, your code looks clean, sequential, and safely awaited. But underneath those friendly coroutines sits a heavily optimized callback-driven engine dealing with messy operating system calls. To understand how your Python application actually talks to a network, you need to look at transports and protocols. These two abstractions form the foundation of async I/O networking. They always work as a pair. The protocol handles the application logic, deciding what bytes to send and how to interpret incoming data. The transport handles the mechanics. It does not care what your data means or how it is formatted. Its only job is figuring out how to push those bytes over the wire. Today, we are focusing squarely on the transport layer. Think about what happens when you write to a non-blocking TCP socket directly. You have to ask the operating system if the socket is ready. You have to handle partial writes if the network buffer is full. You have to track which bytes actually sent and which ones need to be tried again later. An async I/O transport hides all of this complexity. It acts as an opaque wrapper around the raw socket and the underlying operating system calls. You generally never instantiate a transport yourself. Instead, you call an event loop method to create a network connection. The event loop sets up the socket, creates the transport, links it to your protocol, and hands the pair back to you. Here is the key insight. Once that connection is established, the transport takes over the input and output buffering. When your application wants to send a message, it simply passes a chunk of bytes to the transport write method. The transport does not block your code to wait for the network. It immediately drops those bytes into its own internal buffer. The transport then works with the event loop in the background, firing off the non-blocking socket calls to the operating system. If the system can only take half the bytes right now, the transport holds on to the rest and tries again on the next loop iteration. Your application never has to micromanage that queue. Flow control is built right into this mechanism. If you write data faster than the network can send it, the transport's internal buffer will start to fill up. Once it hits a designated limit, the transport triggers a specific callback on your protocol to pause writing. When the buffer finally drains, it fires another callback to resume. On the receiving side, the transport listens to the event loop. When the operating system signals that incoming bytes have arrived, the transport pulls them from the socket and feeds them directly into the protocol through a callback. Everything at this low level is purely callback-driven. There are no awaitables here. Transports also provide standardized methods for managing the connection lifecycle. You can gracefully close a transport, which tells it to finish sending any buffered data before safely shutting down the socket. If things go wrong, you can call an abort method to tear down the connection immediately, discarding whatever is left in the queue. And if your protocol needs to know who it's talking to, the transport provides a method to request extra information, allowing you to peek through the abstraction and retrieve the underlying socket IP address or peer details. The transport abstraction is what allows your async I/O code to remain purely focused on data logic. Transports isolate your application from the chaotic mechanics of non-blocking I/O. They take raw bytes from your protocol and silently handle the buffering, retries, and operating system socket calls needed to move them across the network. That's all for this one. Thanks for listening and keep building.